dramatically when I first attended a workshop at the Aspen Center for Physics, and that I think most of the physics that I've done that I enjoy and I'm proud of has always been at something like the Aspen Center for Physics or the KITP, so I feel especially privileged to be allowed to speak here today. One of the things that I most enjoyed about those venues was the opportunity to interact informally with physicists of all different characters, all different generations, all different research interests. And one of the things that I most appreciated at the Aspen Center for Physics was an informal rule that no one could give PowerPoint talks, that everything had to be on the blackboard as a means of expressing everyone's personality and keeping things informal. And since I think that that's an essential ingredient to the success of this kind of endeavor, I'm going to give a blackboard talk. So I just want to start out by saying that I'm going to give a rather idiosyncratic view of the naturalness issue in light of the Higgs discovery. I think that that's a proper thing to do at this point because I believe that there is something that we really are misunderstanding or have misunderstood for quite a while. And now is the time to start asking questions about that. And so I hope that what I have to say is a bit provocative and not easily accepted, because I think that that will lead to maybe some better discussion. So I'm not going to rely on any particularly precise measurements of Higgs properties. Everything I have to say follows really just from a few simple observations of the Higgs that I think we can all agree are well established. First, the mass of about 125 GeV. I should say that I think that this mass was a surprise to many people and a shock to some who were not expecting Higgs this light, or Higgs at all, for some of my colleagues in any case. And I want to point out that our understanding of electroweak superconductivity, all of the ideas that we have had for its origin have been colored in one way or another by naturalness, really almost since the introduction of electroweak superconductivity. And that the LHC discovery of the Higgs has radically changed the way we need to think about this issue, in my opinion. So now is the right time in this brave new world to re-examine and refine the arguments that we have used to guide our thinking about beyond the standard model physics for the TeV scale. And hopefully, if we think about them in the right way, we can understand in what way they might be inadequate, which hopefully will provide us a certain amount of freedom in thinking about different things. So I want to start in a place that isn't always the natural starting plate for discussion of the electroweak scale, and that is the Wilsonian view of renormalization, since I think it provides the clearest way to think about the naturalness issue. Our theories are specified by some Lagrangian, and in addition, some momentum scale lambda. And that's inevitable. We can't describe the Lagrangian without also describing the scale lambda. And that all observables at momenta less than lambda are then described by an action which is a sum of coefficients that depend on lambda times a set of all possible operators. I've chosen the C's here to be dimensionless, so I've pulled out a factor of lambda which is related to the dimension of the operator. So all scales, so all coupling constants, are measured in terms of the physical scale lambda. The trick for Wilsonian renormalization is that the most convenient thing to do for physics at a scale p is to choose the lambda from that previous equation to be the scale p. Having done that, then all observables are just given by p to some power appropriate by dimensional analysis. If you're measuring a mass, for example, you get p times some dimensionless function of the dimensionless variables c. Of course, in choosing lambda to be any particular scale, we can arrange to use the action at a different scale by renormalizing the parameters in a way that all physics is independent of the parameter lambda. So I just want to do some simple examples that we're all familiar with before I get to the real heart of the matter. So I want to start with probably the most interesting example, gauge theory, a non-abelian gauge theory, where I've included in the action just the usual kinetic term trace g squared with a coefficient c, which in a conventional normalization is 1 over the gauge coupling squared. So of course I mean this in the sense of Wilson that I mentioned a moment ago. There is an intrinsic scale lambda, so we only include physics at lengths at momentum scales below lambda, and we can easily construct a differential equation that the coefficient c satisfies as a function of lambda, called the renormalization group equation. In this language, the variation of c with respect to lambda is just a constant, b over 16 pi squared, where b is some pure number of order 1, and famously it is positive, indicating that this operator g squared is going to scale in a particular way. C goes like a logarithm, lambda over f, plus some arbitrary constant. Since it was a linear inhomogeneous differential equation, this is easily solved. I can rewrite it where I pulled out the constant c at the scale f times 1 plus b over 16 pi squared c times the logarithm. And now, since I've only computed this at weak coupling and perturbation theory, at this order in perturbation theory, that's entirely equivalent to writing this as the constant c times a power lambda over f, where gamma is just some number that's small, because I've done the weak coupling expansion related to that parameter b and the weak coupling c. So notice that famously, as I decrease lambda, the coefficient c decreases as well. In the conventional language, c is 1 over the gauge coupling squared, so this implies that at small lambda, the gauge coupling is getting strong, famously asymptotic freedom, which leads to all of the interesting features of QCD. Another way to say the same thing is that the coefficient of the operator trace g squared has a coupling c which is getting small in the infrared. That is, trace g squared is an irrelevant operator in the infrared. And that is, the fluctuations in the gauge field are becoming less suppressed at long distances. So those large fluctuations are an indication of strong coupling. But the takeaway message here is that in this simple example, the coefficient function c simply scales like a power of lambda, and in fact, it's this simple calculation which leads to the explanation of the proton mass divided by the Planck mass, for example, that David mentioned earlier. As another example, I just wanted to consider a scalar field with a Yukawa coupling to a fermion, and I'm going to ignore all other couplings. In this case, I've called the Yukawa coupling C sub y. We can easily write down the renormalization group equation. In this case, it is similar, although not exactly the same. I've sketched the one-loop diagram that leads to the equation that the variation of c with respect to scale is some other constant b over 16 pi squared times the coupling q. Again, easily integrated. So 1 over the coupling squared is a constant minus b over 16 pi squared log lambda over f. And by the same argument of weak coupling, that's equivalent to c is equal to a constant, again, times lambda over f to a power, positive power. So as in the previous case, this operator, the Yukawa interaction, gets weaker in the infrared. It is an irrelevant interaction, but it still scales like some power of lambda. And now we come to the heart of the matter. If I do exactly the same analysis, including a mass term for the scalar, so I've pulled out a factor of lambda squared by dimensions, leaving me with a coupling constant c, and I've included just the Yukawa interaction, although it's easy enough to incorporate the gauge interactions or anything else, and write down the renormalization group equation. It is, again, very similar. Lambda d by d lambda plus 2 times c. That plus 2 is just a reflection of the lambda squared that I pulled out, is equal to b over 8 pi squared times the Yukawa coupling squared, and again, the equation that an undergraduate can integrate. In this case, there are two terms that appear in C, one which scales like 1 over lambda squared, and then another term which is a constant proportional to the Yukawa coupling squared. Now I say a constant, but that's because I'm ignoring the running of the Yukawa coupling at this order in perturbation theory. Of course, if one were to correct that at higher order in perturbation theory, then that term would also have have a small power of lambda. Because that will be appearing quite frequently, I'm just going to combine all of those coefficients and numbers into a quantity that I'll call R, and notice that we can then write the coefficient of the mass term as some parameter A over the scale lambda squared plus R. So the first thing to notice is that unlike the previous two cases, at small lambda, this coefficient is getting large because of the first term. Also at small lambda, the second term, that constant, becomes irrelevant compared to the first. I should point out that if we were to ignore the term R, which I'll refer to as the running term, then when I simply put this back into the Lagrangian, I multiply by the lambda squared, which cancels the 1 over lambda squared. This just says that the mass for the scalar field is, the physical mass is independent of scale, which is what you would expect for that free case. However, unlike the previous two cases, I can't combine these two terms in a way that looks like it scales like some power of lambda. There are genuinely two terms that contribute what you might think of as the tree-level mass, or bare mass term, which scales like 1 over lambda squared, and then another term which has a very different scaling property, R. And that's really the heart of the matter for what is sometimes called the naturalness or the fine-tuning problem, the presence of these two terms which scale in completely different ways. So what that means is if I investigate the physics at one scale lambda, where one of these terms may dominate, that isn't necessarily true at any other scale. In particular, at high scales where lambda is very large, you're dominated by R. At low scales, you're dominated by A. So just to fix things concretely, let's imagine that we're talking about the Higgs. So I want at some scale mu, which is characteristic of the weak scale on the order of 250 GeV, for the coefficient to be minus mu squared, the negative mu squared that appears in the Higgs potential. So if I impose that boundary condition, it's easy enough to solve for C of lambda. It's minus mu over lambda squared times 1 plus R plus R. And I put the 1 plus R in yellow because R is a small number. Remember, it was calculated in perturbation theory, expressed by 16 pi squared. So at weak coupling, that's a small correction and it's not very important. One thing I should say at this point is that what I've done, which is unconventional in discussing this problem, is that I've worked entirely with physical scales. That is, lambda here is not some kind of UV cutoff that I'm going to take to infinity. It reflects the physics at the scale lambda. So the way to think about this equation is that I haven't set boundary conditions in the UV, I've set them in the infrared, where we know them by experiment. That seems like a better thing to do now that we have discovered the Higgs and actually know what the parameters at that scale are. So you should think of this as being set by the physics at the scale mu, and then this tells you what is happening at scales above mu at lambda. Notice that in this case, as one goes to larger and larger lambda, C approaches the constant value R. So if you were to think about this in the conventional way where you impose a boundary condition in the UV, the only way to obtain the Higgs potential that we know at low scales is if the coefficient C is finely tuned to the special value R, which remember was determined by the Yukawa coupling that I put in earlier. And that's really just what we mean by the fine-tuning problem. In particular, if you want C of lambda to be accurately described by the theory that I wrote earlier, that Yukawa coupling at scales lambda, the higher lambda, the closer you have to tune C to that running value R in order to get the Higgs mass to come out right. So the measure of that fine-tuning is at the scale lambda, C must be R plus a small correction, no larger than mu over lambda squared. So the measure of this fine-tuning, delta C over C, is mu over lambda squared 1 over R. And saying it this way is really a reflection of the fact that if you believe the theory in which I calculated this, which is to say just the Yukawa coupling and no other physics, then the higher the scale at which you believe that is an accurate description of nature, the more finely tuned the theory is. And I think now is the appropriate time to say things this way, because we actually know something about how well at given length scales the world is described by the Higgs and its associated gauge and Yukawa couplings. So we can now plug in numbers and say how finely tuned this is. So for me, the definition of fine-tuning now is that the higher the scale lambda at which we trust the theory that is described by the calculation that I've just done, the more closely the UV boundary condition must match the low energy running. So by measuring the low energy running, which I emphasize is entirely accessible to experiment, we can then decide how finely tuned the theory is. So it's now an experimentally accessible issue defined this way. I should point out that that doesn't mean there's anything wrong with the theory that is finely tuned. That's a theoretical question, whether that's bad or good, but we can still assess what the issue is by experiment. So I just want to emphasize that because occasionally there is some confusion among theorists and experimentalists. The way I've defined the fine-tuning problem is entirely physical. Everything that appeared in the relation on the previous slide can be measured, at least in principle, in experiment. So this is not something that can be solved by appealing to a particular normalization or regularization schemes or measurable quantities which don't depend on those issues. And so we decide whether it is something we need to worry about or not. Okay, so if we believe that fine-tuning in this sense is something that we want to avoid, and I will come back later and address the question whether it is something we should avoid or not, physicists have largely come up with two categories of solutions to this problem. The first is eliminate the operator that had the bad scaling behavior. It was phi dagger phi that had the two terms that appear in its scaling at low energies, which caused the problem. So if we could eliminate the operator phi dagger phi from the low energy theory, then we wouldn't have a problem. There would be no coefficient for normal. The other category of solution is to eliminate the bad scaling. We have one term which scales like 1 over lambda squared, and another term which, in this approximation, is scaled like a constant. If we were able to somehow eliminate that constant scaling that I called R, then once again, there wouldn't be any problem. And so the second category of solution is to use symmetry principles to eliminate that scaling. The first category of solutions are those in which there is no operator phi dagger phi for the simple reason that there's no phi. That is, there are theories that don't have a Higgs in them at low energies. The first example of such a theory is Technicolor, and I'm actually going to just define, at this point, Technicolor to be theories that do not have a like Higgs. I think that's a sensible definition. It isn't the one that Steve Weinberg used this morning. I think he was considering theories that simply have strong coupling, and I'll distinguish those from Technicolor, and I'll discuss those separately. The theories that don't have the bad scaling because of symmetry principles themselves fall into a number of categories. The most commonly discussed one is supersymmetry, but there are other examples. I think all of the other examples that I know of fall into the category of the Higgs being some kind of pseudo-Nambu-Goldstone boson, and I will discuss both of these cases in the context of what we know. Now, there are actually two other ideas that you hear discussed, not so much a few years ago, but since the discovery of the Higgs, because this problem has become sharper, they are now being discussed more and more. One is called composite Higgs, and the other conformal symmetry. I will talk about the composite Higgs in some minor detail. I'm not going to mention the conformal symmetry issue until the very end. So in order to address this carefully, I just want to summarize the properties of the Higgs from experiment that we'll be using. So the first, it has a mass of about 126 GeV. The second is that it has large couplings to the W and Z. As Maria showed, the measurement of Higgs to WW star and ZZ star is convincingly within the standard model range, and by that I mean within a factor of 2. I think the experiments are clearly much closer than a factor of 2, but that's really all I care about. The problem is that if the Higgs is a particle that is the physical Higgs, the 126 GeV particle that has been discovered, is, if we consider the coupling of the Higgs to W's and Z's, since that physical particle does not carry an electroweak charge, it has to either couple like the mass term, according to the Higgs mechanism, or it would have to couple to electroweak invariance. Coupling to electroweak invariance have to go through higher dimension operators, and consequently we give very small branching fractions into W, W star, and Z, Z star, in fact, unobservably so. So the fact that we have observed them is what I mean by large couplings to the W and Z. The second thing is that there are observed small couplings to gluons and to photons. Again, the production cross-section of the Higgs through group fusion is very well established experimentally, and the decay into two photons also well established experimentally. And by small couplings here, I mean, in fact, the contrary of the argument I just gave for W, W, and ZZ, that is, the coupling of the Higgs goes through higher dimension operators because they are color, and because the object is color and electromagnetically neutral. So the W and Z couplings are consistent with the mass coupling, and I think that is what says this is a Higgs. If not the standard model Higgs, it is certainly an object that couples to electroweak symmetry breaking in a big way. And I think that's firmly established by the experiment. And that's the property that we will need. The couplings to gluons and photons is consistent with the large Yukawa coupling of the top quark. I'm going to actually assume that it is arising from the top quark. I think that that's the least well established of the properties of the Higgs that I'm using, but I doubt you would find any experimentalist or theorist who genuinely doubts that coupling. What this implies, since we know that the Higgs couples to electroweak symmetry breaking, is that the top mass is then electroweak symmetry breaking in origin. That is, it looks like the way the top mass works in the standard model arising from Yukawa, a large Yukawa coupling. Finally, there's one other property, not directly of the Higgs, but established by the LHC and other experiments, and that is that so far there is no other new physics, at least up to some scale lambda. And of course, new physics in different channels has wildly different values for the scale lambda at which we have excluded it. But for my purposes, really in the context of Higgs physics, it's many TeV, where many is at least 3 and probably more than 3. Of course, in some channels, it's significantly more. So how do all of these things fit together? Well, they tell us that it is a light Higgs, that is something that has to do with electroweak symmetry breaking, and that immediately rules out category 1, technicolor. That is, we now know there is the operator phi dagger phi that we have to worry about in the theory. So technicolor is no longer an option. We know that Yukawa couples to the top with a large Yukawa coupling, and that means that the running that we calculated on the previous slide is definitely present from this Yukawa coupling. So that suggests that we do have the issue from the previous slide. Of course, we have to ask whether there are any other contributions to the running, and the absence of new physics up to many TeV tells us that modulos of things I will say in a minute, that the calculation of the running is dominated by the top Yukawa coupling, and then we really know the value of that parameter R that appeared in C and lambda earlier. That was the source of our problem with fine-tuning. So I think this is really the point, that why things are so different now is that theorists were able to weasel out of all of these issues until the LHC has firmly established these 3 properties, that it's a Higgs, it Yukawa couples strongly to the top, and that there appears to be nothing else that could modify the running beyond what we calculated. So given the scale of a few TeV with no new physics, then we can plug into the relation that I had on a previous slide, and by that definition of fine-tuning, the Higgs mass is finely tuned at the percent level. Now, of course, when the LHC turns back on, the scale lambda will go up, or we will find new things, one or the other. If the scale lambda goes up, the fine-tuning gets worse. So in fact, with the LHC, it could easily be the case, assuming that no new physics is seen in an appropriate channel, that this fine-tuning goes down below the level of percent to a few tenths of a percent. I think that's what the LHC will be able to do in its current configuration. Okay, so if Technicolor is not a viable option, what about supersymmetry? Well, in particular, supersymmetry evades the problem of the fine-tuning by having a symmetry which cancels the contribution to that running R from the top quark. Of course, that symmetry relates the properties of the top to some scalar particles, the right-handed and left-handed stops. So the running that we have calculated, I remind you, is from the Higgs mass up in scale. So it has nothing to do with what's going on at the gut scale or any particularly high scale. It's entirely from 125 GeV up to that several TeV range where we haven't seen any new physics. So the absence of stops tells me that I have correctly calculated the running in that mass range. And therefore, my 1% fine-tuning is a fine-tuning even in the context of supersymmetry. Well, provided the stops are truly absent. If one looks at the latest limits from ATLAS and CMS, generically the limits on stops are about 600 GeV, 700 GeV. So I looked at the latest ATLAS paper where they said 600. In any case, that's a bit less than my few TeV, so if I simply plug in 700 GeV, the fine-tuning is at about the 6% level. Now, does one want to call 6% fine-tuning? I'm not sure, but I'll come back and discuss that in a minute. But actually, I think more significantly, is the light quarks, the limits are significantly better. In fact, they are at least a TeV and larger in some cases. So there is then a loophole in the naturalness argument for supersymmetry, which I think is important. First of all, you may not worry about a 6% fine-tuning, and so if we should see a stop well below a TeV, that would be a good sign for supersymmetry, and that is still perfectly possible at this point. So I think anyone who is announcing the death of supersymmetry as a solution to the naturalness problem is premature. But what is potentially more interesting is that the stop could actually be lighter than 600 GeV or 700 GeV. While the limits generically are 600 or 700 GeV, there are places where stops are especially hard to see. When they are very close in mass to the top quark, for example, where they tend to be soft, and there is a window of opportunity there. Notice that that would remove the fine-tuning entirely. Of course, the fact that the other superpartners have not shown up and the limits on them are significantly better without these loopholes would mean that we're in a situation where the stops are light and all the other superpartners are heavy. So this remains the only part of the supersymmetric parameter space which actually addresses this fine-tuning problem. Now I should say that there's another problem, the hierarchy problem, which is not what I'm discussing in supersymmetry. I have nothing to say about that at this point. I'll make a comment about that towards the end. But supersymmetry may or may not have something to do with that. But I'm only interested in what happens at these very low energies. Of course, the suggestion that the stops are light and all the other superpartners are heavy now goes by a name. It's called natural SUSY, not in the sense that Maria and Joe were using the words. Actually, natural SUSY was an idea that was invented for no particularly good reason in the late 90s by Ann Nelson, David Kaplan, myself, and Savas Dimopoulos and John Giudice, which lay dormant, I think, for a long time until the discovery of the Higgs, where it remains a loophole, which my own opinion is it's likely to get closed. I don't think it's likely that we're going to find the light stop. Okay, the other possibility is a Nambu-Goldstone, pseudo-Nambu-Goldstone boson, and indeed theories of this sort are divided into two categories. One of them is called composite Higgs, a really terrible name, which first appeared on the scene sometime in the late 80s, I think, early 90s, and has been revived significantly in the past year or so. Although there are lots of things that go by the name composite Higgs, again, I'm going to be careful and define exactly what I mean. Composite Higgs theories are pseudo-Goldstone bosons with a natural scale of natural F constant, the analog of F pi, of 250 GeV, and they then become strongly coupled at a scale of a TeV. So the constraints from experiments are now such that there is no indication of strong coupling at a scale of TeV. The absence of new physics up to a scale of many TeV implies that these kinds of theories can't work unless there's some kind of accident. And what I mean by that is there are some cases where if one calculates the scale at which the coupling gets strong, rather than being 1 TeV, it turns out to be 3 TeV because there's a numerical factor that appears. And of course, if one then looks carefully at whether that is consistent or inconsistent with the data, if that accidental numerical factor is adequately large, it might be okay. That's a situation where this is not then a solution to the fine-tuning problem. It just says, well, the fine-tuning problem wasn't a problem to begin with, it was just an accident. So if we were at 6%, I think no one would be upset about that being an accident. If we were at 1%, I think a lot of people would be upset and a lot of people wouldn't be upset. If we get down to a few tenths of a percent of fine-tuning, then I think you'll see a lot more worry. But in particular, my interest as a beyond the standard model builder is constructing explanations for the fine-tuning rather than just having it arise by accident. So this is a possible way that nature works. It's not something I want to consider for the moment. So the other category of composite Higgs models goes by the name of little Higgs. And the distinguishing feature here is that the pseudo-Goldstone bosons remain weakly coupled well above the TeV scale up to a scale of about 10 TeV. There is a technical mechanism imposed to do that, which the details are not very important. But since they remain weakly coupled up to 10 TeV, they remain viable, at least for the moment, as a possible explanation. However, in order to remove the running, the dangerous running, they also need some kind of partner of the top quark that comes in to cancel the running that we calculated earlier from the Yukawa coupling of the top quark. For little Higgs theories, this is a top prime particle, which is a colored fermion with quantum numbers basically the same as the top quark, and there are very good limits from the LHC on T primes. In fact, the generic limits on T primes right now are, again, on the order of a TeV or so. There are some specific limits in certain models that are well above this, I think up to 2 TeV now for T primes. Electrically charged colored fermions are pretty easy to see, so the limits are quite strong. There are certain special cases, just as in supersymmetry, where the limits are significantly weaker. And so the little Higgs theories, I think, are slightly more disfavored, in my opinion, than supersymmetry at this point, just on the basis of the limits. But they could be right. There's still room for this loophole where the T prime arises for a certain special case. And I actually think that this is worth theorists considering, trying to construct models in which you get T primes that might be lighter than the current limits and that can evade the current limits. So ultimately, I'd say this is about the same as SUSY, maybe not quite as good at this point, but not significantly worse. Neither of them looks great. Neither of them is totally ruled out. But there is, I think, an important implication of this discussion. And the reason that I tried to make it in this simple way is that there's a litmus test for whether or not nature has a solution to the fine-tuning problem, this small fine-tuning problem of 1% or something that might get as large as 10%. As far as I know, there is no solution to the problem that does not have a partner of the top quark to cancel the dangerous running that we had before. So this is the simple litmus test for whether or not nature has a direct solution for this fine-tuning problem. If we do not see top partners, then the fine-tuning is either an accident or a misunderstanding on the part of theorists. something that is worth saying in the theory community and in the experimental community as well, because it's a significant target for us to understand naturalness, and I think that we should be saying this more. So what are the implications of all of this? Well, so beyond the experimental implication that we should be heavily focused among our other experimental efforts in searching for top partners, both scalar and fermionic, it's important to realize that naturalness has been the guiding principle behind our attempts to understand the physics of the TeV scale. I mean, it was one of the original motivations for supersymmetry. It's the motivation for composite Higgs. Sorry, not the original motivation for supersymmetry. It is one of the motivations for supersymmetry of the TeV scale, was to stabilize the TeV scale. Now, the hierarchy problem, which supersymmetry can continue to solve, that is to eliminate the running well above the TeV scale, which I'm not addressing here, is still, I think, an excellent motivation for supersymmetry at relatively low energies. And I think that's important to keep in mind. It doesn't imply that supersymmetry has to appear at LHC. So I am actually still a fan of low energy supersymmetry, but if low energy supersymmetry exists, it no longer has anything to do with what is sometimes called the little hierarchy problem, the fine-tuning issue that I'm discussing here, unless light stops are found. But the model building efforts at the TeV scale, say at energy scales between 1 and 10 TeV, have been strongly influenced by the motivation to solve this fine-tuning problem. And so it's important to realize that, well, we can first establish the status of this by experiment. That's being done, and I think that that's one of the important lessons of this discussion. We do that by searching for top partners as the #1 priority. Establish the running. Remember, I've emphasized that this running is experimentally accessible, so our experiments by measuring the Higgs couplings can tell us about that running. We need to establish it firmly. And we can then ask, well, what do we say if the fine-tuning is established at the 1% level? Which I think we're pretty close to that. Well, the first thing we can say is it's an accident, as I mentioned before, and I think a number of physicists have suggested that then you would want to test it at the 10 to the minus 3 or 10 to the minus 4 level. The 10 to the minus 3 level is something that is barely accessible at the LHC. 10 to the minus 4 level is hopeless for the LHC, and it has led some people to call for a 100 TeV collider in order to assess that. I think it's a bit premature to jump to that level, but it is something that people are talking about. More interestingly, I think, is the idea that naturalness is just wrong. We've used it as a guide for our model building efforts at a TeV, and if we find that the fine-tuning is genuinely there at the 1% level or less, then we have to seriously accept the possibility that our arguments for naturalness are wrong, and that has, I think, huge implications. So first of all, without naturalness as a guide, we really don't have any particular expectations for what physics should look like at the TeV scale, and that's great news for model building. Because it's a license to think about all sorts of things that previously, when you would give a seminar on them, people would say, well, that's finely tuned, that's not natural, I don't want to listen to you. And I think that, well, if naturalness turns out not to be something that is realized in experiment, then we should stop using it as a bludgeon for those theorists who want to consider things that aren't natural and aren't finely tuned. So I think that, in fact, in many ways, this is the big lesson for me in the Higgs discovery, is that we should start thinking about things differently. And so I think that a lot of the ideas that are getting pushed back from the community about conformal symmetry and other exotic ideas are exactly the kinds of things that we should be focused on right now. Because we don't understand what's going on, assuming that naturalness turns out to be a problem, and so we need to be looking at things in a different way. In addition, there is this notion that there's a separation of scales. The Wilsonian approach tells us that the short distance physics only appears in the long distance physics through the determination of some of the couplings associated with the relevant and potentially marginal operators. And really, that's the essence of the theoretical argument in favor of the absence of fine-tuning, is that we should not have a conspiracy of the UV couplings with the IR. And the running I've been talking about here is entirely in the IR. In order to achieve the Higgs couplings that I've described, the UV value of C has to be finely matched to the running, whatever it is. And that's why I didn't worry too much about the details of that value R. If the running is somewhat different, well, R is somewhat different. But still, you have to match all of the running. And that means if there's any physics beyond the TeV scale, any new physics, well, then the UV would have to know about all of that physics between the TeV scale and whatever scale you're opposing the UV boundary condition in order to match it. And I think that's just contrary to the Wilsonian ideas of the separation of the UV and the IR scales. Without this separation between UV and IR, I think it completely changes the way that we want to think about model building at low energies. And in many ways, that's liberating. So really, that's my conclusion for theorists, for model builders, is that we should stop being so timid, that we should consider lots of things that previously were anathema, that since experiments are beginning to call into question one of the most used guides to TeV scale physics, we should recognize that it was just a guide. It was a clue. That clue might be wrong. And so we have to take seriously the possibility that it is wrong, and that means there's a lot more to do. So really, in this case, ignorance is an opportunity. And I think that this was something that David said earlier. It's a coincidence that I use the word ignorance, is that he said knowledge leads to ignorance, and that's a good thing. And that's been the status of the standard model for a long time, where we thought we understood renormalization and the fine-tuning issue, and maybe we were wrong. And being wrong is a good thing. Thank you very much.
Well, thank you very much for a suggestive talk. And any questions? Oh, yes.
Big light is even better.
Yes, I was.
I wasn't. Comment. So I'm glad to see that naturalness, you're announcing naturalness to some extent, because the one thing that people tend to forget, you say it was a guiding principle. Naturalness has never been a principle. It's never been a principle. Principles in physics are well defined. It's been a strategy.
Yes.
And strategies fail, and it's no big deal. So, it's always bothered me that people are upset with the 1% naturalness issue with respect to, but not with the 10 to the 9 naturalness issue with respect to the ratios of Yukawa couplings or fermion masses. Now, those are logarithmically varying, but at whatever scale you define, you have to specify those Yukawa couplings. The small numbers involved in those are 10 to the minus 8, 9, right? Something like that. Spectrum, quark and lepton masses.
Even more than that. Yeah.
And that's true at any scale because they only vary logarithmically.
Right.
Why isn't that an enormous problem in naturalism, which has led us nowhere?
Right.
We have faced that problem for 30, 40 years, measured those parameters over and over again.
Strategy, that's the word.
Strategy, perhaps we need to change our strategies, and those strategies can have all sorts of inputs. They can be ultraviolet inputs, they can be symmetry inputs, or something new. That's another comment.
Can I actually make a comment about what you just said?
Yeah.
So first, you're completely correct, and that the word strategy, so I'm going to adopt from now on the word strategy. I did not mean to imply by principle that it was some established property of the theory that we wanted to demand.
We have principles in physics are things that you can test.
Right, like the equivalence principle.
There's no way of testing naturalness.
Well,
and once you understand something, you know, those of us who lived through the adoption of the so-called standard model remember how unnatural it appeared to most. Steve sort of alluded to that. There were people who regarded the SU2 course U1 version of the vector weakly as incredibly ugly and unnatural. It's not, after all, a not a simple gauge group. Why would you do something like that? So, but once it's established experimentally, it seems awfully natural.
Well, you invent a notation to make it look nice. Right?
Yes.
Now it fits on T-shirts, which it didn't originally.
So,
No, but I wanted to actually say, so the issue, there are actually many different things that people refer to as the naturalness problem, and I think that that's unfair, that there are different things. And all of them are questionable whether they are actual problems or they're just things that we have to learn to accept. So the issue of the small numbers in the ratios of Eucalip couplings, for example, are, I think, not of the same character as what I described here.
they're even more mysterious.
They are even more mysterious. I think that's exactly right. In some sense, this is also what Steve was complaining about with supersymmetry and the mu parameter, that supersymmetry, even if, let's imagine that stops are light and that solves the problem that I was discussing here, Steve would not be satisfied because he wants an explanation for why the weak scale is so different from the Planck scale. So this removes the running, which means there's no fine-tuning at each stage, but there is a new parameter, which is the ratio of the weak scale to the Planck scale, and one might wonder why that parameter takes on the value that it takes on. And I think that that's an excellent question. And the Eucalip couplings are in the same category. There's no running issue, but why should nature have these very tiny parameters? In the context of the axion, I actually wanted to say this is why my quip about it being as finely tuned as the thing it was trying to solve, because it's a new intermediate scale, and there's no reflection of that scale in any way. So why would I want to extrapolate a theory up to the Planck scale? Because nothing at low energy indicates any other scale except the Planck scale. And that's actually why I'm not so fond of the axion, because it would be yet another scale at which there's no hint of it at a low energy.
You also remarked that some people, to remain unnamed, are trying to sell 100 TeV machine on the basis of naturalism, which I think is an extremely misguided advertising campaign. Try to convince a politician that naturalism is natural. Naturalness is a description of physics. It's just crazy way of selling it, seems to me. What we should, at least among ourselves, sell a 100 TeV machine is that we're trying to determine the scale of the new physics. The best way to determine it is to go to that scale and do experiments. And 100 TeV is perhaps within reach. And that's, if there's new physics there, then that's the scale. We're not looking for natural feeling good.
So I couldn't agree more, and I hope that it was clear from my tone that while I would love a 100 TeV collider, I'm fairly derisive of the naturalness argument that people are using to push it. And I also completely agree with you in something that I have been saying, as you have been saying for a long time now, that the issue is scale. That is, the purpose of these experiments is to establish what the physics is at the given scale. And that, that's how we should be selling these experiments, for the scales that they can probe. That's what makes the ILC such a good argument for the scales that it can probe, and that's what makes a 100 TeV collider a good argument.
Yeah, so I would ask, can you turn the problem around and say that the quadratic divergences, for example, is a solution to something? And what I'm thinking about, in other words, instead of thinking of it as a problem, say that it's a solution to something. And what I'm thinking specifically is, how do you connect? We have, as you said, we have the Higgs, we have the measured mass. How do you connect it with the electroweak phase transition? from the other side, let's say, and I think these, together with biogenesis and the connection with dark matter, and perhaps getting out of all this, the way you said it is, I think, it gives me confidence, because I think so far I have heard it only from two people in this room, Joe and David, and I thought that it might take 10 years before I heard you saying that, so that we might give up, that we might actually think that naturalness is wrong, and that these guiding strategies based on the experiment we have to revise the way we think. So this is a very good thing that you said it, but can we also try, given what we see, to figure out what are the other connections?
Well, so two comments. So first of all, I'm a bit offended that you would think that I wouldn't.
No, I don't mean,
this for years.
Yeah, okay, so I don't mean you in particular. I mean you, the theory community. I don't mean you, Andy.
I think
Yeah.
that there is a large part of the theory community who shares
so
this
this,
view.
so that
But I will
think,
acknowledge that there's also a large part that doesn't.
Okay, so the larger part is the one I was talking.
Yes, and now the better the physics question is, can one actually make use of these
Yes.
things? And I think the answer to that is yes. But that will take us kind of far afield. Maybe we should talk about that in my project.
More questions? No? Okay, so